Good afternoon. So Jerry and I are from Databricks. Thank you for coming. Today we're going to introduce a new feature in Spark to allow you to implement real-time applications. Real-time is a very popular word. I searched data plus AI submit and see how many sessions have real-time in its title. And you can guess. There are 25 sessions have real-time in its titles. So real-time is a really popular word. So today we're going to talk about the Spark new features. This talk is going to be a technical talk. We're going to dive into the technology, how this one can be implemented. Tomorrow there will be another session, and Jerry and Kartik will give the session tomorrow at 3 o'clock. The session is called Delivering Sub-second Latency for Operation Workload on Databricks. This is not counted as a part of 25 talks. It doesn't have real-time in its name. You can search Jerry Peng for his name, and you can find the session tomorrow. So today we're going to talk about this new feature. What? No. Which direction to go? Oh, okay. So first we're going to give some introduction to Spark Streaming, and then we talk about why we need to build this new mode and how we build it. And in the end, we'll give some demo to prove that this is a real thing we have implemented. So first of all, Spark have streaming capabilities. Some people might not know or know. This is the definition in this official page saying structured streaming is a scalable and fault-tolerant stream processing engine built on the Spark SQL engine. So remember, scalable and fault tolerance. It's also mentioned they have several of characteristic subsystem. It will process it incrementally. It means as soon as some data comes, we will process it continuously. It never ends. So keep going, new data coming, we process it. And we'll update data as data continue to arrive. We don't wait for the end or something. As soon as we have data, we will output it. Right? Just remember, fault tolerant, scalable, incrementally, continuously updating data to arrive. Right? There's one word it's not mentioning it at all. Not mentioning at all. This word is latency. Right? It didn't mention actually. How long it takes from input to output it is not mentioned. So let's look at the latency looks like for the current system. So some brief introduction how it's implemented. It is implemented in the so-called micro-batch architecture. In this way, data is cut into batches. Actually, every batch is processed like a batch query. For each batch, in the planning phase, it figures out what data it needs to process. And in the execution phase, it reads that part of the data and then process it and output it. So what does this latency look like, or say freshness? Because of this architecture, for every batch, the data's process is actually arrived mostly in the previous batch, right? Because that's how, when the planning phase, we can see the batch. So what's the latency means? The latency is at least a batch duration, right? It's, because it's processed the previous batch data, the worst case is arrived in the beginning of the previous batch. And furthermore, because most of the time the output is actually generated in the end of the batch, so we sometimes see the batch duration to be maybe close to 2 batches. Why? This is the end of the generate the data is output by the end of batch. One of the reasons is that the batches are executed in stages, and these stages are run in sequential order. Only one stage finishes, we start another one, and we start another one. So data is only generated in the last stage, and there's also scheduling overhead, coordination overhead, so that all of these are counted as part of each of the record. So how to how to make this fast? One way is like we just speed up everything, scheduling stages. So every batch duration is like 100 milliseconds, so the duration could be less than 200 seconds. The way we did is we create a new way called real-time mode. We rethink, we don't do this micro-batch way anymore. This feature is right now in public preview. You can try out. Lots of queries can be supported. You can talk to your account team and see how to try it out. We are also going to open source it. We got proven by the Spark PMC, and in the following months, we will open source it. You will be able to use it in open source. So in this new mode, we're targeting the ultra low latency, or say freshness in another terminology. In micro batch mode, we usually targeting to a second level. And the real-time mode, we're targeting a sub-second level to be 100 milliseconds or even lower. So these applications will be useful for some use cases, such as like Internet of Things, and then like fraud detection, or some of the online applications. Well, again, you can come to tomorrow's session. Jerry and Karthik will give some introductions to how these things can be solved real-world problems. So basic idea about this one is rather than try to shrink this batch smaller and smaller, we make the batch longer so that the scheduler overhead is amortized. But on the other hand, the data is streaming out inside of batching without batching end. So let's give some of the basic architecture. So remember the previous graph, we process the current batch process data arrived from previous batch. In this case, is a batch running very long, and then this most recent data is processed as it comes, and then it's flow all the way to the process engine, and then get to the output. So we run the batches in fixed long durations, usually minutes, and by default 5 minutes, and the data can flow from the source to the end without any buffering in the middle. So there are some major changes we make to this architecture. First one is we need to turn these stages from sequentially scheduled to they are concurrently scheduled. At the same time, we modify the source so that instead of read as fixed ranges, we would read the freshest data as it comes. And then we modify the shuffling so that the data is shuffled as it comes. And we also schedule the stages in concurrently. In order to achieve that, we need to change the way we do checkpointing. In micro batch mode, the checkpointing is done as in the planning phase of a batch. We determine the data we would like to process by looking at the start and end offset, and they are written to the checkpoint. And then we do the execution, and then in the end, in the commit phase, we write to a marker saying this is committed. If the query is restarted before it's committed, we will replay this batch in the same way by looking at the logs. And then if the query restarted after commit, and this is considered done, it would not be replayed. But in a new mode, when we start this batch, we don't determine the end of the batch. We just keep processing all of this fresh data. Only in the end of processing, we look at what offset we have processed to, and then at that time, we know this batch's start and offset. And at that time, we write to the checkpoint location and together with the commit log. So in this approach, only in the end, we know the start and end of offset. But this approach creates a problem because in the previously, a batch is idempotent. No matter how many times you restart it, it will process the same amount of data. So that a state store checkpoint is idempotent. Right now, in the new approach, in the real-time mode approach, state store checkpoint is not idempotent anymore. So in order to resolve the problem, we create a new way to do state store checkpointing. Every checkpoint will be attached to a globally unique UUID, and then that ID will be committed, will be written in the commit log so that we know that which one is actually committed. So there's no confusion. So putting things together, we made some major changes to checkpoint mechanism to make it possible. We changed this offset writing from the beginning of the batch to the end of the batch, and then we also changed the state store checkpointing to have a globally unique ID, so that it could be attached to the actual commit. But by the way, this one we call checkpoint v2 is also be a good thing for micro batch mode too, and in the future we will also make it default to the micro batch. Only make this shuffling and source reading in streaming order sometimes is not enough. Sometimes operators also need to buffering. If we don't change that, the operators will only output in the end of the batch and will be slow. So we need to modify some of the operators so that data are streaming. So the one we modified is so far is aggregation and some of the UDF operator. And also there's transformer state operator. That's new. I think there's a talk today. I hope some of them join that one. That feature, by the way, match this real-time mode very well. And we also implement the real-time mode support for this feature. So also there's a problem for state cleanup. State store is the storage to keep track of data across all of this processing, even if the query is restarted in the past. But the state store, you cannot keep data forever, or you have to clean it up after a while, if not useful. Previously, we clean up by, in the end of every batch, we scan the whole state store and then see whatever it is need to be cleaned up, we just delete it. This is obviously will introduce long latency in real-time mode. In real-time mode, we kind of doing this incrementally. We're spreading this cleaning up overhead to the whole 5 minutes. After processing every row, we scan state store for several rows and see whether there's anything to delete, and if there's anything to delete, we delete it. And then we process another row, and then we scan state store for another several rows. By doing that one, we can spread out this state store cleanup job across the 5 minutes so that it doesn't impact individual rows' latency. Yeah, so that's the summary what we did. We did this as a long time-based execution. We scheduled the stages concurrently. We implemented source so that it reads most fresh data. And then there's a streaming shuffle. It's a major change to the shuffling so that it can stream in the data in shuffling. And then we changed the way we do checkpointing by changing the offset from the beginning to the end. And then we changed the way we do state store checkpointing to have unique ID. And we also changed the operators to reduce buffering and do the incremental state cleanups. So this is one again. This is available in public preview. Talk to account team to try it out, and it will be open source soon. And I think Jerry is going to give a preview.
Hi everyone, I am Jerry. Is everyone still with me? Or everyone's still, okay. So now let's talk about kind of the API that allows you to use real-time mode. It's super straightforward, super simple. Currently, when you run a query, structured streaming query, it looks like that, right? You have your read stream, you have maybe some transformations, you have your write stream, which is you're writing it out. In this case, you're reading from Kafka, writing to Kafka, and then maybe you specify the kind of trigger type here, processing time trigger, which is the default one as well, if you don't specify anything. So how do you enable real-time mode? That's it. You change the trigger, you get lower latency, and I will show that in the demo as well. And that's really all it is in real-time mode for the user, is basically switching the trigger. And that's one of the things that we intentionally built into real-time mode to encourage users to use it, is basically the seamless user experience that you're able to switch between processing time trigger, trigger available now, and real-time trigger. We understand that users, like yourself, have different needs often, right? Sometimes you want to have cost optimization, you want to have and prioritize throughput, but maybe something changes in the future, right? Now you want to more focus on latency. You can change basically your trigger from, say, trigger available now, which is more like a periodic incremental processing. You run it every so often, but it's very cost effective. But you want to run that now with low latency, simply change the trigger. So let me go over kind of the processing semantics. That's one of the interesting topics as well of real-time mode. Pretty straightforward as well. We guarantee the same processing guarantees as the existing kind of execution modes, like the micro batch mode, right? Same exactly once processing guarantees is maintained. We can get into a whole talk about what exactly is exactly once, but here is a best attempt at summarizing that is each input record affects the final output exactly once, right? So that is maintained. Let me talk about end-to-end guarantees. So for end-to-end guarantees, or exactly once end-to-end, exactly once delivery, however you want to kind of describe this, it's really sync dependent as well, right? You have to kind of have support in your external sync to basically get that exactly once. Often is have some transactional support, or you're able to do idempotent writes. For real-time mode, we currently support, the sync that we support is Kafka, and for each syncs, which for each sync allows you to, it's an interface, an operator that allows you to write essentially wherever you want to write to. You're given a row, go write it somewhere, wherever you want to do. You're allowed to basically create custom syncs that way. Of course, you're also able to use the data source v2 API if you want to have the full breadth and depth of APIs to write a very complex sync. You can also do that as well. End-to-end exactly once, if you're interested, it can be guaranteed, right? But you obviously have to be able to write to that sync in an idempotent way as well. So it can be done, but there's some extra work that might need to be there. But for Kafka, the existing execution modes supports exactly once, at least once as well. So we're not really changing the guarantees there. So let's talk about performance, right? We're talking about real-time mode, right? We're talking about it delivers ultra-low latency. How do we actually compare with kind of the existing execution modes there, right? So here is a graph. We've ran several kind of benchmarks of common kind of patterns or queries that we have seen. To be honest, these are actually old numbers. The newer numbers are actually better. If you go to the keynote on Thursday, Michael Armbrust's keynote, he will actually share some newer numbers, hot off the press, that are actually even more impressive. But the general idea is we see 2 orders of magnitude improvement in latency with real-time mode. All right, let's go over the demo, which is honestly the most exciting part for me. So, if you were sleeping through the talk before, or you're trying to push a commit, this is the part to really listen to, because it really demonstrates kind of the power of real-time mode, and it really allows you to visualize exactly what we're talking about here. So let me first go over kind of the scenario of the demo. The demo is a continuous environmental monitoring scenario. So imagine a city where there are sensors. It's not very hard to imagine, I would guess nowadays, that continuously monitors environmental conditions across different locations and zones. Each sensor collects measurements such as, say, temperature, humidity, CO2 levels, particulate matter levels that are 2.5 micrometers or lower. And what the city administrators want to do is, one, say, multi-parameter threshold monitoring, real-time detections of basically of violations of these sensor readings such as temperature, humidity, CO2 levels, and so on and so forth, around the city, right? Another thing could be real-time, alerting, right? immediate notification when there are changes to an environment, so city administrators can react to those situations accordingly in a timely fashion, right? Another thing could be monitor real-time trends, right, in analytics. What are the trends? Are these measurements rising, decreasing? What is going on with basically these sensors, right? So let me also go over kind of the pipeline we have crafted for basically the demo. We're basically using Kafka to Kafka. The source topic is Kafka, the sink topic is Kafka. Imagine measurements are being basically gathered from all sensors and published to a Kafka topic, right? They're read by an Apache Spark query. It's a two-stage query. The first stage, you can think about it as a map stage, parses the data, right? And then we do a group by location because we want to do some analytics on a per location or per city basis. And we use the operator here, transform with state. As Sing mentioned, there was already a talk today about it. It's our new basically custom state API that basically allows you to do powerful stateful transformations with the data. And then with that, we can basically send alerts, trends, and aggregations to basically your downstream Kafka topic that then you can use to send out alerts, power dashboards, so on and so forth. So let's get to the demo. I guess we can play it.
The demo to showcase real-time mode and structured streaming. This whole demo is implemented on a Databricks notebook. Let me first walk you through the setup. I have already configured a Kafka cluster to be deployed that is reachable by this notebook. I have also started a data generator to generate data to be sent to the source topic of this Kafka cluster we are using. First, let's inspect the data. What is the shape of the input data that we are going to process in this demo?
Maybe I should have come up with a joke. It takes a little bit to, it's real because, it's actually trying to load it here.
You should edit it out.
Huh? Or speed it up, right? Yeah. But we're good on time, so, we can.
This is not real-time mode, so
this is not
okay.
That is being continuously generated into the source topic. As you can see, these are the columns. There is a key, and there is a value, and then there's some metadata information such as source, such as topic, partition, offset, timestamp, and so on and so forth. But let's take a look at the value here. This is where actually the sensor data that I mentioned before is shaped. There is a sensor ID, there is a location, there are temperature readings, there's humidity readings, there's CO2 readings, and also particulate matter levels as well. And each one of these readings has a key, and we're basically continuously sending this data into the source topic to be processed by our query shortly. So let me stop the query that reads from the source topic and go to the query we have here to actually process the data and send out meaningful alerts and analytics. So I've defined some data structures that my query is going to use. Here's a case class that describes the input, the data shape of the input, sensor ID, location, city, and so on and so forth, and the different measurements that the sensors will provide. I have another case class here that is state. This is basically data that we are going to persist into the state store of transform with state to keep track of a historical list of data that we can use for analytics such as trends and averages and other sort of aggregations. Here is the output, and this is what we're going to output from the query. It contains the sensor data, the input basically, the row input of the query, and also kind of the analytics, some of the aggregations such as daily average, temperature trend, high temperature count, and any sort of alerts that are produced in which any of these kind of readings such as temperature, humidity cross a certain threshold, and we want to alert on those high readings from the sensors. And here is the definition of the stateful processor, really the meat of the query here. We're using transform of state, and really the query, like I alluded before, is simply storing storing rows of data to calculate basically trends and aggregations, and also based off of these thresholds to send out alerts if certain readings are above a certain threshold. So you can see the code here. We're storing basically historical data. We are also using that to analyze trends, and subsequently we are basically checking the current temperature to see if there are any sort of alerts that we need to send out. And we are outputting our data here. Let me actually run these. And then, let me run this again. And now let's actually run the query here that I have defined that reads from our source topic and writes to our sync topic here that basically deserializes the JSON, passes to the transform and state operator that we're using for our alerts and analytics, and writing it to a Kafka topic here. First, let's use the existing processing time trigger that already exists today for structured streaming. And even if you don't set a trigger, this is basically the trigger that it will default to. So let's wait for the query to run. Let's go over to another notebook that can basically read out the results. So I have a notebook here that's basically reading from the sync topic, and it's basically going to output what is written in the sync topic, as well as latency that the record took, that Spark took to process the record. And how do we define latency here? We define latency as the time the record was first persisted into Kafka, or the log append time of each input record and the source topic, and also the log append time of each record when the structured streaming query writes to the sync topic. So we're really computing the time that has elapsed for this record when it was written to the source Kafka topic and when it was written to the sync Kafka topic. So let's run the query. As you can see, we are getting the results now. We have each row has a sensor ID, location, city, timestamp, the temperature readings that were part of the input, but now we're also computing a daily average temperature, which is basically using the data that's persisted in the state managed by the engine via transform of state. It also computes a temperature trend, whether the current reading contributes to a falling, a stable trend, or a rising trend. Here's the number of actually high temperature counts that we've computed as well. And some alerts, such as, for example, this alert has a high CO2 alert, also a high particulate matter alert, so on and so forth. And the last column here is latency, which I want to talk a little bit about more. As you can see, the current latency for processing each one of these records, you can see is about, around 1 second, right? This is the latency we're getting with the existing processing time trigger, or the existing kind of execution mode that produces the lowest latency possible in the existing engine. Now, let's simply switch over to using real-time mode. Let's restart the query. Start it again. So now, all we really need to do for starting the query in real-time mode is simply change the trigger, and you can seamlessly switch between other processing modes in structured streaming to real-time mode. Okay, the query is running. Let's switch over to see what the input is. So now you can see the input in the existing triggered processing time mode was around 1 second. We restarted, so there was some high latency. But once we really transition to real-time mode, we can see that the latencies are now in the low double-digit milliseconds. So compared to the existing processing time trigger, we have basically 2 orders of magnitude difference here. The latency in real-time mode is 2 orders of magnitude smaller than the latency that's able to be produced by processing time. And that's really the cool thing about real-time mode. You can seamlessly switch queries between different execution modes and immediately see the difference in latency. This is all I have for the demo. Thank you for listening in, and hopefully this gave you a glimpse of the...
Okay, all right. So hopefully this gives a great demonstration of real-time mode. If you're interested, like Seeing mentioned, 1, please come talk to us about your use case. Number 2, you can talk to your basically account team of how you can get onboarded to real-time mode as well. And I guess we have time for Q&A.